Ready? All right. I think we're up. We're on YouTube.
Okay.
Ready?
I'm just going to bring in my list.
We put lights down when we start.
Okay, about time.
There's not be a lot.
Where's the mic?
Lot of backgrounds.
Where's the mic? Second mic? Oh, you got the mic. As long as you got yours, that's. Hello, it's about that time. So we're gonna change things around tonight. My name is Tom Nolasco, I'm president of the club. And we're changing the order of things tonight. We're going to have the main speaker who's going to speak first because she's on a time crunch. So we're going to have her go, and then we'll go through the club business and the observing talk and all that second. So without further ado, I'll let Jeremy introduce the speaker.
All right. Thanks, Tom, and welcome everyone. First, a quick update on upcoming. This is cutting out on me a little bit. All right, quick update on. Talk loud. A quick update on upcoming programs. In March, we're going to have Dr. Erin Crail from Kutztown University. She'll be talking about Mars. Then in April, we'll have Dr. Matthias February from Villanova. He's going to be talking about his research on binary stars. And later in the summer, probably July, we're going to have Bart Fried. He'll be coming to visit us. And I believe September will be our picnic at Fort Washington. Everything else is TBA so far. All right. So it gives me great pleasure tonight to introduce Dr. Ekta Patel. She's an assistant professor of astronomy, astrophysics, and planetary sciences at Villanova as of this year. So Ekta did her undergraduate degree at NYU in physics, did her graduate work at the University of Arizona, did a postdoc at UC Berkeley, and was a NASA Hubble Fellow working at the University of Utah. So her research interests involve galactic dynamics and dark matter, particularly for nearby and low mass galaxies. So please join me in welcoming Dr. Patel.
Can you all hear me okay?
Yeah.
All right, great. If at any point I'm not talking loud enough, which I usually don't have an issue doing, wave your hands vigorously at me or just say hi. So I know you're still awake. Thank you for adjusting your schedule for me. We are going on spring break this coming week, and so I'm catching an early flight tomorrow. I got to go back to Philly. It's great to be here.
The screen go to sleep.
Oh, wake up. The screen doesn't want to stay awake. Hopefully everybody else does. I'm already doing it. All right, well, let's hope this doesn't mess up our Zoom. Double check. Yeah, the Zoom looks good. Okay, hopefully I won't go to sleep again. As Jeremy said, I think about galaxies, galaxy evolution, galaxies interacting with each other. And that's really what I've been working on for the last 10 or so years of my career. So I'm happy to be here today to tell you all about the kinds of things I think about, or the things that keep me up at night. But it's especially nice to be talking about all of this not too far away from where my journey started. So I grew up just an hour and a half away from here in Bayonne, New Jersey. So it's fun to be back somewhere a little bit more local compared to where all of my various studies have taken me. So I would like to start with a very small disclaimer, which is that by training, I am a theoretical astrophysicist. So please do not take me outside and look up at the sky and point at something and say, hey, what's that? I'll probably say, it's a plane. So by training, that is not my specialty. While I went to graduate school in beautiful Tucson, Arizona, I did not stay up all night at the wonderful telescopes out there, though many of my friends did. Instead, my laboratory is a good internet connection and a high-powered computer. So I will tell you how I use those kinds of tools to study things that we really can't track just by using telescopes, but that we need to build models and simulations to study in addition to using lovely data that we get from telescopes. So I know that many of you have been astronomy enthusiasts, if not professionals, or taken some classes, probably for a long time. But I like to always get started in some of these talks, if my clicker will work, by reminding us about our place in the universe. So I'll play this video that some of you may have seen. We're going to zoom out from the Earth. It's going to go very fast. We're going out to the solar system and the asteroid belt, the outer planets. And then we're going to go to the constellations and the nearest stars. Moving out to the known exoplanets inside of our galaxy. Out to our lovely Milky Way galaxy, that is our home. And I'm going to end this video. It does keep going, but I stop it purposefully at nearby galaxies because that is what I refer to as at least my space laboratory. So I'm going to start even after that with just a very basic definition of a galaxy, because when you think of a galaxy, my best guess is you probably think of images that look like this, or this, or this. There's a whole variety of different structures and shapes and sizes and colors that probably come to your mind. All of these are different galaxies. But what I want to highlight and start this talk off with, and kind of plant in your head for what you might focus on as you continue to learn about galaxies from here on, is that the definition of a galaxy is still somewhat continually changing. The reason for that is because you can ask yourself the question, why aren't these things galaxies? They also have stars. They're also emitting light. They're also gravitationally bound collections of matter. But as you might guess, as we learn more and more about galaxies with better telescopes, better technology, more advanced algorithms, we have to start to redefine the way that we categorize a whole lot of different astronomical objects, like the very sad story of Pluto, right? So we do the same thing with galaxies as well. And this definition has been reworked many times. I'd say the most recent professional definition was only reworked back in 2012 in a paper led by a colleague that used to be down the road at Haverford. Beth Wellman led a nice paper where they came up with a new definition of what is the modern galaxy. So I'll give you the definition of the modern galaxy a little bit paraphrased, which is that for today's talk and for, I think, the current consensus of what we think of as galaxies, is the definition that galaxies are a system of millions or billions of stars, gas, dust, and dark matter held together by gravitational attraction. And I'll come back to this later in my talk because I do think about dark matter a lot, but it's really this little piece here that has been the modified version, at least in the last revision of what galaxies really are. So we'll talk a lot more about that as we move through this talk. But given that definition, it's going to be the one that we work with. That still means that all of these beautiful objects are still what we define as a galaxy using this definition. So on the right side, I'm showing an image from the James Webb Space Telescope. This is showing you a galaxy cluster, which is a gravitationally bound group of thousands of galaxies. And on the left, I'm showing you a gallery of galaxy images. Don't try to say that fast. That represents a lot of the galaxies you might see in the image on the right side. They're not the exact ones, but they give you a sense of the broad diversity that we see when we look at galaxies in general, all across the universe. When we zoom in to individual galaxies, there's also a lot of structure, as you could already see from these pictures. So if we zoom into the components of, let's say, a spiral galaxy like that of our own, the Milky Way is a spiral galaxy, as is our neighboring galaxy, the Andromeda Galaxy. Galaxies also have very distinct components, and those components in the kind of work that I do are very helpful in helping us understand how galaxies built up over time. So in this artist depiction of a Milky Way-like galaxy, which is indeed based on real data, but of course, because we're inside of the Milky Way, it's kind of hard to see the whole Milky Way. Galaxies, like spiral galaxies, have this central nucleated bulge. They have a galactic stellar disk. They have these beautiful spiral arms. In this case, in the Milky Way's case, we live inside of one of those spiral arms in the solar system. And there's also several other components of galaxies that are pictured on the right or drawn out on the right. There's globular clusters. There's something called a stellar halo. I'll talk a little bit about both of those. But there's also a couple of components that are not yet shown here. So these are sort of the basic components of a galaxy itself. kind of ignoring the nearby neighborhood of what else might be surrounding a galaxy. So to start to give you a sense of scale, because this talk is going to be one that requires you to sort of tune your mind to very large distance scales and very high speeds. I'm going to start out by giving you the fact that the solar system is, of course, in an arm that is rotating around the center of our galaxy. And so our solar system is moving around the galaxy at over 500,000 miles an hour, which means that it takes the solar system about 225 million Earth years to make one rotation around the center of our galaxy. Okay, so start to get used to time scales that are going to be on the order of hundreds of millions of years, and then we're going to even go up a step into billions of years in just a second. So this is sort of the distance scale, the speed scale that we're talking about and the kind of work that I do in galactic dynamics. You heard in the introduction and in my abstract that I work a lot on satellite galaxies. So again, I want to just quickly define what it is that a satellite galaxy is. This definition is a little bit more intuitive. It is indeed a galaxy that orbits around another galaxy. In my case, because there are a couple of different definitions for satellite galaxies depending on where in the universe you're looking. In my case, satellite galaxies are typically orbiting a larger and more massive galaxy. So you can think about them as the smaller companions of a Milky Way-like galaxy. So the analogy for a satellite galaxy is very similar to the moon orbiting around the Earth, right? This is a very cyclical process. The moon goes around the Earth every 30 days. Similarly, on very large scales, satellite galaxies are orbiting around their host galaxies. However, it's not always the case that these satellites are moving in a very periodic orbit that follows the same exact path over time. So there's a little bit of a difference between the kinds of paths that these satellite galaxies follow compared to things you're used to thinking about, like moons around planets or even planets around the sun, right? So we know there is some precession in the planetary orbits around the sun, but for the most part, they're fairly periodic and regular orbits that we can trace over time and predict very much to an exact point. Where will Jupiter be in its orbit in 45 days from now or 45.7 days from now, right? It's a little bit harder when we get to the larger scales of satellites and their host galaxies, and we'll talk about why. As I mentioned, we're also going to start moving to these very long timescales. So these timescales where it is necessary to bring in the computers and the models because we cannot sit here and observe something for a billion years because we won't be here anymore. So billions of years, as a reminder, if you're not used to thinking about this unit of time or distance or whatever you want to add a billion in front of, is a 1 followed by 9 zeros. And in astronomy and in other places in life, you may have heard of the prefix giga, especially if you work with computers a lot. We think about giga years, okay? So that's going to be the abbreviation that I use to discuss a unit of a billion years throughout this talk. So start to get used to giga years. You'll see me abbreviate it as this GYR throughout the talk on various images. Okay, so I've told you what a galaxy is, or a modern definition of a galaxy is. I've told you what satellite galaxies are. So let me introduce you a little bit to my space laboratory of what we call the local group of galaxies. So this is also an artist depiction based on real data. And the first thing I want to mention is that this picture is not complete. And a little bit of the reason why it's not complete is because we have been finding so many new satellite galaxies over the last 15 or so years that it's very hard to keep this figure up to date. And we'll get there in just a second. I'll give you a sense of how quickly we've been finding new satellite galaxies, but at least gives you a bulk idea of the satellite galaxies in our local group. Not very cleverly named, but nevertheless, we have our Milky Way galaxy depicted down here in the bottom right. And all of these little blips of light around it are satellite galaxies of the Milky Way. You can see most of them are roughly the same mass and size, at least to scale in this image. There are a couple of them that are a little bit bigger and brighter. And then the same is true when you look up in the top left, that's our neighboring galaxy Andromeda and its satellite galaxy companions as well. And similarly, you can see there are a couple of bigger satellite galaxies in that image, but many of them are quite small and not that bright. There is one other component of the local group, which are what we refer to as some isolated dwarf galaxies. So that's similar to what you see in the bottom left here. I'm not going to spend much time in this talk thinking about and talking about these galaxies that are down here. They're essentially galaxies, dwarf galaxies that we think are not gravitationally bound to either Andromeda or the Milky Way, but they are bound to the entire group as a whole. So they're kind of just orbiting in the periphery around this whole overall system. And I have published many works thinking about those galaxies as well. But for today's talk, we're going to focus mainly on the systems of satellites around the Milky Way and Andromeda. So the numbers I've added onto this plot are indeed more accurate. As of right now, we know of about 60 satellite galaxies orbiting around our own Milky Way. So we've got 60 other companions out there. And around the Andromeda galaxy, we know of about 35 satellite galaxies. But like I said, these numbers are only very recent and have been changing quite a lot over the years. Again, to give you a sense of distance scale, if you think in light years or kiloparsecs, I'm not sure if one is preferred to the other, depending on what your astronomy interests are. But the Milky Way and Andromeda are separated by about 770 kiloparsecs, which is about 2.5 million light years. And then the radius of a local group is roughly a megaparsec, or about 3.2 billion light years, to give you a sense of the scale of these things. So let's talk a little bit about the history of finding these different satellite galaxies. I'm going to focus mostly on the Milky Way, but the story is very similar when we think about the Andromeda galaxy and the discovery timeline of satellite galaxies around Andromeda as well. So I will start with our two brightest and most massive companions, which are the Large and Small Magellanic Cloud. Has anyone seen these from the Southern Hemisphere? Yeah, you're really, really lucky, because I tried once and it did not work, so that was sad. I have studied the Magellanic Clouds pretty much since I started pursuing a professional career in astronomy, and I have yet to make that come true. So there's hope, but we'll see. It was cloudy in Australia the night I had to look, so it was unfortunate. Anywho, I'm glad you've been able to see them. For those of you who have, if you haven't, and you go to the global South in general, look up and try to see them if it's dark enough outside. These are the most massive satellite galaxies orbiting around the Milky Way. While they are called Magellanic, I could go on a very long rant on this being a misnomer of sorts, because it was not Ferdinand Magellan who found these galaxies initially. But as we know, history is depicted in ways that people want it to be depicted in. And so there's a very large push to change the names of these clouds, because they've been very significant to different civilizations all across the global South for many thousands of years before Ferdinand Magellan set sail to incorrectly find the country he was trying to go to. Anyway, moving on. So these have been at least the first two known satellite galaxies of the Milky Way, mostly because they're very large on the sky, they're very bright on the sky, and so people were able to identify them very long ago. So I'm going to show you a figure that now starts to count up over years how we have, and through what means we have, discovered satellite galaxies over time. So on the x-axis down here, I'm going to show you discovery year. So it only goes back to 1920. So I have this arrow here because the Magellanic Clouds have been known for much longer than that. And it ends at roughly present day. And the y-axis is just counting up the total number of satellite galaxies known by that year. There will be two lines on this figure. If you can see them, you can differentiate between the colors. The orange is showing you Andromeda, or M31. And the blue is going to show you the satellite counts for the Milky Way. So when we think about the discovery timeline, if we look at what this figure is already showing us, by just a little past the year 2000, we knew of about a dozen satellite galaxies around both the Milky Way and the Andromeda galaxy. Okay, so now you can start to make the connection that there's been a very quick jump in these numbers. And there's several reasons why. As I mentioned briefly, a lot of this is because of technology and being able to build telescopes and instruments and algorithms that are able to do something much more powerful, which is moving into an era of not just taking photographic plates and looking for satellite galaxies by hand, but taking advantage of digital surveys. So digital surveys are telescopes that will scan the sky many, many times over the same parts of the sky. So you can gain exposure time over those areas of the sky, thereby letting you look fainter and fainter into the universe, or further and further away, or to smaller and smaller sizes, etc. There's a lot of different parameters that can cover. So just after the early 2000s, the first very widely known digital survey, the Sloan Digital Sky Survey. Oh, here's some pictures of some of the classical satellite galaxies. If it looks like there's nothing there, that's intentional. These galaxies are all very, very small. And so even if you don't believe that there's something in those images, I promise you there's a very small little blip of stars in there. If you want to come look up at the screen later, you can certainly do that. But as I was saying, the very first big uptick in the number of satellite galaxies found was due to these digital surveys. So the Sloan Digital Sky Survey, the first results in terms of satellite galaxies from that survey came out just after about the year 2004, 2005. And in that survey, because it was scanning many parts of the sky, being able to reach deeper magnitudes, many, many new satellite galaxies were found around both the Milky Way and the Andromeda Galaxy. So by about 2010, those numbers had quickly jumped up to about almost 30 or 40 Milky Way satellite galaxies that were known, and easily above 20 for satellite galaxies around Andromeda. Then, through even better digital surveys, we had the similar kind of situation. So in 2014-15, results from what we call the Dark Energy Survey, which is a telescope down in Chile, were released. And I distinctly remember when these papers hit the internet, because I was a first or second year graduate student, and I ran over to my PhD advisor's office down the hall. I said, "Did you see these papers today? There's like 15 new satellite galaxies people just found." So it's been quite a fun time to be following this trajectory, where the literal data sample that I'm working with is just growing day by day, month by month, year by year. So by the time we hit 2020, we got very close to the numbers that we now quote. This is very much an ongoing process. We are nowhere near probably finding all of the satellite galaxies around the Milky Way and Andromeda yet. If you're familiar with the Vera Rubin Observatory, which started taking data last year, and some first images were released in the spring or summer of 2025, that telescope, also based in Chile, is going to be revolutionary for finding satellite galaxies in the southern sky around the Milky Way and around, unfortunately not around the Andromeda Galaxy because it's not visible within the survey limits. In theory, we think there should literally be something like 200 Milky Way satellite galaxies. So if we're lucky, we may have gotten a quarter of the way there. This is going to continue to be a very exciting space to work in, because this is such a rich history that only keeps changing on quite a rapid timescale, at least relative to some other areas of astronomy. So I'll show you a couple of other images to give you a sense of the diversity of these satellite galaxies as well, because they are not all the same size, they're not all the same mass. I've written some numbers up here if stellar masses mean anything to you. We call these sort of intermediate mass satellite galaxies, some of the first dozen or so that were found. They're of course amongst the brightest ones. They have stellar masses that are about 10 to the 5 to 10 to the 7 solar masses worth of stars. We have these ultra faint dwarf galaxies, which really just started to come into view with these most recent digital surveys about in the last 10 years. And those are at most about 100,000 solar masses worth of stars. Some of the smallest ones and least massive ones we know of maybe have like 100 solar masses worth of stars. So we're talking about a very broad range of what it is that we define as a satellite galaxy. In the case of the Milky Way, essentially all of the satellite galaxies are defined as a dwarf galaxy. So just meaning that they are small and not very massive compared to the Milky Way itself. Okay, I'll show you some more sizes to give you a sense of the range again. So on the right side, I'm showing you one of the most diffuse and low mass satellites in that most recent sample that was discovered. Again, probably doesn't look like there's a whole lot. Maybe if you're up close, you see a very, very faint smudge. And then on the left side, you see the Large Magellanic Cloud, which is again, the most massive and brightest satellite galaxy of the Milky Way. So there's a whole lot of diversity in between here. And it's really going to be these objects that are at this end that are going to continue to push that definition of what is a galaxy, especially as we collect more data with the Vera Rubin Observatory, and maybe have to start again to redefine what exactly are we calling a galaxy versus not. But that's a talk for another day, maybe in another 5 years. So I have given you a lot of definitions so far and sort of introduced you to the tools, at least the astronomical tools that I think about. So I wanted to stop briefly and see if there are any quick questions, if you've missed anything so far, if you want me to repeat or clarify anything before I go into the real meat of the talk on why do we care about these satellites. So I saw this hand go up, yeah?
How do you know a galaxy is a satellite galaxy?
How do you know a galaxy is a satellite galaxy? That's a very good question. So that will hopefully become a little bit more obvious in the second half of the talk. So I'm going to wait to fully answer that question. Was that your same question?
Yeah, same.
Okay, so yeah, that is a lot of what I do, and so I will hopefully answer that question. If I don't answer it fully enough, please ask again. Jeremy?
I thought it was interesting that there were more known satellites of M31 than
Yes.
of the Milky Way.
Yes. That is because on average, they are bigger and more massive. So we think the Andromeda Galaxy itself, even though it's often thought of as a twin of the Milky Way, it is also brighter and more massive. So even though it's far away from us, on average, because those galaxies are bigger and brighter, we can still find them a little bit more easily than some of the Milky Way satellites. So at the faintest end, for example, of what we do know of the Milky Way satellite population, we have yet to find those around M31. Yeah. Yes.
The smallest satellite galaxies,
Uh-huh.
are there minimum mass
Yeah,
definitions.
Yeah.
They're getting pretty small.
right. They are getting pretty small and they certainly actually cross over into the range of what we think of as like a star cluster. There's an overlap there. And that definition sort of changes between a star cluster and a galaxy, mainly because of dark matter. And so there are a couple of different properties that start to change in that overlapping mass regime, where that overlap is roughly in the area of about 10 to the 4 to 10 to the 6 stellar mass. But the smallest satellite galaxy we know of is in the range of like hundreds of 100 or a few hundreds of a solar mass worth of stars. Yeah. So quite small, quite small. Now, that doesn't mean that that's all the mass that's in them, but it's the mass that we have detected thus far, right? So when we find a satellite galaxy, we might not be detecting the whole thing. We might just be finding the brightest stars in that galaxy. And so we start with that and then we refine from there. Good questions. Okay, I don't see any other vigorously waving hands, so I'm gonna keep going. Okay, so for the rest of the talk, I'm gonna tell you about why are these satellite galaxies important? Why are they useful astrophysical probes? What can we do with them, etc. So I will give you a handful of reasons. I will say this is not an exhaustive list, but I think they're some of the most interesting ones that you may be hearing about in the news. They're also some of the ones that I work on, so in my biased opinion, some of them are interesting reasons. But I will start with that the faintest satellite galaxies that we know of around the Milky Way are really fossils of the early universe. So these tiny little things that we can barely measure the properties of are really some of the things that formed first in the universe. So this is a very compressed timeline of the universe, which we know is 13.8 billion years old. And I'm teaching a class that's called How Old is the Universe? And many of my students have not yet learned that number, but they're going to. But we know the universe is about 13.8 billion years old. And many of these faint dwarf galaxies formed their first stars, or all of their stars, really in that first 1 billion years after the Big Bang. Okay, so that's what I mean when they are really relics or fossils of the early properties of the universe. Okay, so some of the earliest stars to ever form in the universe, we think formed in these very small galaxies that we now find in our galactic neighborhood. Okay, so that's alone very exciting because it's hard to learn about the early universe. We can only peer back so far, even with the best telescopes. And so being able to have nearby little pieces of evidence, just like real fossils on the Earth, tends to be quite helpful in learning more about that era of time. So that's one reason. Another reason, and one of the really main ones that drives a lot of my research, is that satellite galaxies you can think of as the building blocks or the Legos of galaxies. So we think in the universe that the process of galaxy formation and evolution occurs in the process shown on the right, which is that small galaxies form first, and then over time they merge and form a slightly bigger galaxy with more mass. And then they merge again and they form yet another more massive, bigger galaxy. And that process continues many, many times over. And that number of mergers that exist per galaxy varies depending on how big that final galaxy is today. But in general, we have this hierarchical structure where the small things combine together and form something bigger. And this is exactly how we think our Milky Way formed. We think our Milky Way has merged with something like a dozen other galaxies over its roughly 10 billion year lifetime to reach its current properties, its current mass and size and structure. And as these mergers happen, you might be able to pick this out a little bit in some of these different branches if you follow them down. That also causes these galaxies to end up with different shapes than they originally started with, right? Of course, different sizes and mass, but you also get evolution of what we refer to as morphology, or the shapes and structures of these galaxies as they're merging with each other over time. They don't have to merge with an equal mass galaxy. Galaxies can merge with something much smaller than them, much bigger than them, equal mass galaxy, etc. They are very agnostic to what kind of galaxy they're merging with. Gravity is really doing the dominating work of making them merge together and coalesce into one bigger galaxy. Okay, so these satellite galaxies contribute very much to this process because as satellite galaxies start to become gravitationally bound to their host galaxies, eventually what we think happens is what's depicted on this left image. So this again is another artist's illustration of real processes that we have observed, where it's showing you how a satellite galaxy has over time lost many of its stars in this very ordered ribbon-like pattern, where you can go back and see the different traces of the orbit of this satellite galaxy, and eventually it will just merge into its host galaxy. So these ribbons of stars are what we call stellar streams. These are observable. There's already a few dozen known around the Milky Way. The Sloan Digital Sky Survey, as I mentioned, has been very helpful in finding the first stellar streams around the Milky Way. We see these stellar streams and satellite galaxies, I should have said this earlier, ubiquitously in the universe. So it's not just the Milky Way and Andromeda that are special. We see these around other galaxies as well. And so that's how we really can confirm this theory that galaxies are building up over time through this process of smaller galaxies essentially being eaten by their friendly, larger neighbors. Okay? So satellite galaxies are very crucial to this process. They become bound to their host galaxies. Over time, they essentially give in to the gravity of their host galaxy. They lose stars in this process, leaving behind these stellar streams. And eventually, that smaller galaxy will just become a part of its host galaxy. And as time passes, what happens is that the stars from those satellite galaxies, the smaller ones, end up just getting mixed into that main host galaxy. So if enough time passes, for example, the Milky Way's earliest mergers, it's quite difficult to pick out where which satellites they may have come from originally, or group them together based on when a merger might have happened, especially if it was very, very long ago, because they kind of just blend right into the population of Milky Way stars that we see as at present. But more recent mergers, so when satellites have disrupted, maybe just in the last couple of billions of years instead of 10 billion years ago, there tends to be some of these traces left behind where their remnants can tell us something about the orbital path that they followed as they merged into that central host galaxy. So they give us all these nice clues as they're in this process of merging. Okay. I'm going to show you a video which puts this into motion. It's going to be a video of a simulation. So it's not going to be real data, but it is rendered to look like real data if you were able to point a telescope out at a Milky Way-like galaxy and watch it for billions and billions of years. You're going to see this process of many mergers happening over time. So it is specifically a galaxy meant to resemble a Milky Way-like galaxy. And you'll see, and I'll try to point out, different satellites sort of falling into the gravitational sphere of that Milky Way-like galaxy and being consumed by it, sometimes after one pass, sometimes after two passes, sometimes it takes multiple passes. Do you have a question before I keep going? Or is that just a hand? Okay, good. All right, so let's take a look at this video. This was run by some of my colleagues at Rutgers. So you have this very bright central ball. It's meant to represent the Milky Way-like galaxy, and all of these ribbons are meant to represent these stellar streams. These smaller balls of light are these satellite galaxies. You see simultaneously, there are many of them approaching the central host galaxy. And you see as they fall into the center, some of them make it back out and they leave that ribbon of stars behind. This dramatic one leaves behind these tidal tails and eventually forms more of these long stream-like structures. But overall, this is a very, very much an ongoing process. Many of these can happen simultaneously, but do note that this timescale is very, very long, right? So it's already gone up to 13.8 billion years. So that's a little bit of it in action. So imagine that happening over and over and over. If we look out into the universe, we see pictures like this, right? So these give us snapshots of galaxies merging together, but it's quite difficult to actually understand what will happen in the future and what has already happened in terms of the interaction between these two galaxies. Right, so this is useful as a starting point, but we really would love to have that kind of movie going back and forth where we can rewind and fast forward how these mergers and these interactions are occurring. And that is where a lot of what I do starts to come in. But I did mention dark matter earlier in my talk, and now is the time where I have to bring it back because it turns out to be something that's very important when we think of the components of a galaxy and how we model galaxies to end up with movies like the one I just showed you. So, satellite galaxies are important also because they live inside of a dark matter halo that surrounds their host galaxy. So this is showing to scale. You might wonder, why is that little galactic disk so tiny? But I did it on purpose to show you that this is meant to represent the actual visible stellar part of a galaxy's disk of stars. And this is meant to represent the reservoir of dark matter that we think it might live inside of, in size, right? So these dark matter halos are almost 20 times the radius of these very bright galactic disks that you're used to thinking about when you think of a nice picture of a galaxy. So satellite galaxies, if you think about them orbiting around a host galaxy, and that host galaxy has this giant reservoir of dark matter around it, those satellite galaxies are essentially tracing the sphere of that dark matter that is around that host galaxy. So you can think of them as, dandelion seeds flying in the wind, right? You don't see the wind, but the seeds will follow the wind patterns, right? Same idea is happening here. The satellite galaxies will be orbiting through the dark matter halo of their host galaxy. They also have dark matter halos of their own, but I'm not going to focus on those today. And so they act as a tracer. They can tell us about this dark matter, which we frankly don't really know a whole lot about. So they help us measure properties of this dark matter that we don't really understand. I'll tell you why we think it exists in a slide. But essentially, dark matter is this invisible matter. It does not interact with baryonic matter. Baryons are a fancy way of saying all those stars, gas, and dust that emit light or absorb light, or both. But dark matter only exerts gravity. It does not interact with the light at all. So we can only determine things about dark matter by watching how satellite galaxies, for example, are moving through this dark matter halo that is surrounding in an invisible way those host galaxies. Okay, so they help us really try to put together some puzzle pieces where we cannot directly observe something ourselves. So we use them as an indirect way to probe something that we think is there that we cannot see with our eyes or with telescopes. Okay, in the Milky Way, and this is generically true, the Milky Way's dark matter halo and galaxies' dark matter halos overall is actually where most of the mass in a galaxy lives. So it's not the stars, it's not the gas, it's not the dust, it's not these nice, pretty spiral arms where most of the mass in that galaxy lives. It is this vast reservoir of dark matter that actually makes up the total mass, a majority of the total mass of a galaxy. So that's about 85% of a galaxy like the Milky Way. I already said that these dark matter halos have extents that are much bigger than those nice, pretty galactic disks. And so we can't just ignore this dark matter when we're trying to understand how these satellite galaxies are moving. Because remember, we can't just point up at the sky and trace these satellites over time and then nicely draw out their orbits. We have to use models and simulations that I'll get into very soon. I'll stop to say a little bit about why we think dark matter exists, and I'm just going to give you one reason, but there's much literature on this. You may have already heard about this from other folks. One way we think that dark matter exists is because of Vera Rubin. So what she did is she looked at the rotation speeds of stars and spiral galaxies, and she tracked them. So she looked at our neighboring Andromeda galaxy, for example, and she tracked the rotation of stars in the center, and then further from the center, and then even further from the center. And these data points back here are her data points on what was actually observed for the motion of stars in the Andromeda galaxy. And you can think of a spinning disk of stars in a galaxy or in a spiral galaxy very similar to a pinwheel, right? If you put a dot on the center or very close to the center of a pinwheel compared to a dot near the edge of a pinwheel's spoke, they're not going to move at the same rate. The dot that's in the center is going to go around the center of that pinwheel much faster than the dot that's at the end of the spoke. The same exact thing is happening in galaxies, at least in spiral galaxies. So what that means is that her observations did not match the underlying expectation for the physics of how stars should be rotating in a spiral-like galaxy. So as you move further and further from the center, she found that speeds increase and then they kind of plateau. They go down a little bit, but then they kind of plateau and stay relatively high, even in these very dim regions in the outer disk of the Andromeda galaxy. But this is what was naively expected just based on basic physics, where you would have an increase in speed and then it would slowly decline all the way down to zero as you hit the edges of the galaxy. What that means when you try to interpret that and make sense of it is that there has to be some invisible massive matter in those areas in the outskirts of the galaxies that is not emitting light, that is causing the speeds of the few stars that are in the outer disk of this galaxy to rotate faster than expected. Okay, so there are many, there's this large reservoir, like I said, of these dark matter halos in these spiral galaxies. She studied many spiral galaxies and she mapped out the same exact pattern in every single one. The speed was always higher in the stars near the edge compared to what was expected naively from the basic laws of physics. So this is one reason why we think dark matter exists. There are many more in the literature now, even though we still don't really know what it is. We don't know what the basic fundamental dark matter particle is made of. There are a lot of good competing theories. There are many telescopes, or rather I should say detection experiments, both on the ground, underground, some in space, that are all trying to figure out the answer to the same question. And I'd say we're making a little bit of progress in that we're ruling out various theories, which is always good. But we're still a little bit away from actually figuring out what that matter is. I'm going to leave the dark matter mystery there, but what I will hope that you take away from this talk and moving to the rest of it is that we cannot simply ignore the dark matter when we're modeling galaxies and trying to understand the orbits of their satellites. So let's come back to the local group of galaxies. And I'll tell you about what I actually do with this nice laboratory of all these satellite galaxies. What I try to do is figure out that. These are all orbits, or representing orbits of many of the different galaxies in the local group, many of these different satellite galaxies. And they are all actually real data. I've kind of done my best to sort of orient them in the right way and put them onto this figure, which is projected a slightly different way than I typically will make these visuals. But the point is that we're trying to understand, how are these galaxies moving relative to each other? What do they tell us about the formation of their host galaxies and the evolution of their host galaxies? Which satellites are interacting with their host galaxy or another satellite galaxy as everything's orbiting around each other? So we're really trying to break down those little puzzle pieces and understand how this whole group of galaxies came to exist in this gravitationally bound group and organize the way that they are presently. So I'll now tell you a little bit about how do we actually come up with these orbits. So I'm going to show you one slide that has one set of equations on it. They're not even written out, but if anyone likes the math, this is for you. So how do you actually reconstruct the orbit of a satellite galaxy? So I've mentioned a couple of times that you have to build a model that's generally representative of what we think a galaxy is made of and how that matter is distributed. So we have our galactic disk and bulge. The bulge is representing that nucleated cluster of stars in the center of the galaxy. The disk is that sort of flat pancake-like shape that's rotating and full of stars. And then we know that we have these dark matter halos. And because work is very much ongoing in trying to understand the properties of these dark matter halos, I very simply modeled this dark matter halo as a sphere. I've at least tried to attempt to give this sphere non-uniform density, meaning that I have colored it darker blue in the middle to try to represent that we do think there's more dark matter near the central parts of the galaxy compared to the outskirts. So it's not just the same everywhere, it's distributed differently. But we don't really know if they're spheres. So this alone might not be an accurate representation. In fact, we're pretty sure they're not spheres. And that's a whole other thing I can tell you about in another different talk. But for the purpose of trying to reconstruct these orbits, we start with the most basic thing first, right? So we model these different components of the galaxy. We have some equations of motion that describe the mass that's in the different components of the galaxy and how those satellites will move through that gravitational potential, right? So you can think of this as just mostly our basic gravity. Forces, two things are attracted to each other. We calculate velocity and acceleration. So this is a fun little derivative up top where each of these terms is describing how the mass is distributed in the bulge of the Milky Way, how the mass is distributed in the disk, how the mass is distributed in the halo. And then there's one more thing that we have to account for. I mentioned how these satellite galaxies act as tracers of this dark matter halo. And the fact that this dark matter halo has mass associated to it and quite a lot of mass means that satellites, as they pass through these dark matter halos of their host galaxies, will also experience something called a drag force, which you may have heard of, be familiar with already. We experience it here on Earth if you're in an airplane or a car and there's wind and you're passing through. This is the idea that as these satellites are passing through the dark matter halo of their host galaxy, particles start to crowd around right behind where they are, slowing it down a little bit. So because they're moving through a massive medium, they are slowed down a little bit by that mass. So they're still going to move because they have their own gravity and they've got a velocity, but you do have to account for the fact that the dark matter will slow them down a little bit. So that's the very basics of how we model a galaxy and the kind of math that goes into it. It's a lot of orbital mechanics and calculus. The other key piece of information, so I've harped a little bit on how we really need models and simulations to do this kind of work, but we do need a piece of observational material, actually a couple of different pieces. And I will tell you about what that information is. So we need first a distance measurement. So let's say we're interested in the satellite galaxy Draco. So we have to measure a distance to the Draco galaxy. We do this by measuring the relative brightness of stars. We know that there's a very standard relationship between them. So that's not quite a difficult measurement to get. We know the distances to many objects in many galaxies. So let's just say we've got that in hand. No big deal. We also need to understand how that satellite galaxy is moving, right? Everything is orbiting around everything. And so we need at least an initial place to start in terms of how is that satellite galaxy moving relative to our Milky Way? Which direction is it going in and how fast is it going? So we can start to measure at least some of this velocity information by measuring the spectrum of a star. So that's essentially you collect the photons of light that are coming from that satellite galaxy, and it'll tell you something about the motion towards or away from us, or really either one. So that gives you what we refer to as a line of sight velocity. So it only tells you the motion from your reference point here on Earth towards the line connecting you to the object we're talking about. So that's a good start. We have a one-dimensional distance and a one-dimensional velocity. But the universe is 3D, right? It's not enough information. We need a little bit more. So what we have to do is we have to take an image of the stars in the Draco Dwarf Galaxy now, and then we have to take another set of images after some amount of time has passed. And when you do that, you can derive something called a proper motion. This is the angle of motion across the sky in a certain amount of time. So essentially, it gives you the other two dimensions across your plane of the sky instead of just towards and away, right? So the line of sight velocity comes from measuring photons collected from that star. But the proper motion, you take two sets of images, you look for the difference between the motions of stars in those images, you identify the same exact stars in each set of images, you take the difference between them, and that gives you an angle of motion across the sky in those other two dimensions. This is the part of the equation that is not easy to measure. And I'll show you a demonstration of that and why in just a second. But this is the difficult part. These two, pretty simple to get. But the great thing is if you happen to have all three of these things, you then know how that satellite galaxy is moving in full 3D. You know exactly what its position is in 3 dimensions, and you know exactly what its velocity is in 3 dimensions. So now we know how it's moving relative to our own vantage point here on Earth. Now we've been able to measure proper motions in a variety of different ways. So I work very closely with observers who obtain this kind of data and reduce it to try to tease out these very small motions. And they use observatories like the Hubble Space Telescope, the Gaia spacecraft, and even long baseline radio interferometers on the Earth to measure these proper motions for different satellite galaxies in the local grid. As the history of discovery has rapidly increased, the amount of data that we now have for proper motions of these satellite galaxies has followed similarly. So there's a few-year time delay in new satellite galaxies are found. A few years later, we try to measure their proper motions. The game gets a little tricky as you go further away. Because you notice I said you have to wait a certain amount of time between taking these two images. And the reason is because if you don't wait long enough, you won't really see a difference in the motions of those stars or in the change of location of those stars on the sky. And so the distance to a satellite galaxy determines exactly how long you have to wait between those two sets of images to actually measure a proper motion instead of just getting 0. So for Milky Way satellite galaxies, given the distances of them, we can wait something like 3 to 5 years between taking two sets of images, and we can measure proper motions decently well. When we go to the Andromeda system, the situation gets a lot more complicated because it's far away. And even though it's our closest neighboring galaxy in terms of the size of the Milky Way, a neighbor in that sense, it's still far enough that measuring a proper motion is difficult. You have to start to wait 5 or 7 or 10 years at the distance of the Andromeda galaxy to measure these equivalent motions in stars orbiting around, satellites orbiting around Andromeda. So to give you a sense of what this whole idea of measuring a proper motion looks like in practice, I'm going to play a little movie that will actually show you how the proper motion of the Andromeda galaxy was measured for the very first time. And this was only done in 2012, so still really not that long ago. Up until 2012, we had no idea how the Andromeda galaxy was moving in full 3D relative to us. We only knew how it was moving in the direction connecting us and Andromeda. So we're still learning a lot about even our nearest neighbors. Okay, so what's going to happen is I'm going to play this movie. There's going to be a time clock, I believe in the bottom left as I start to play it. This is just giving you a relative scale of how big the moon is on the sky relative to Andromeda, which you can see from the northern hemisphere. And what will happen is, as the movie starts to count up in time, we're going to zoom into this blue field of stars. I know it does not look like that will contain stars that are a part of the Andromeda galaxy, but take my word that even though the main body of Andromeda is nicely illuminated here, even as you go to distances out here, there are still stars that are a part of Andromeda out here. So we're going to zoom in to this field, and as the time counts up, you're going to see the drifting across the sky to simulate taking two different sets of images and looking at the difference in motion of the same exact set of stars in that blue field. So let's watch that. Notice the time clock will start at the year 2012. So all the bright white points are stars in Andromeda, and you notice there are some background objects that look stationary, like these background galaxies, right? They're so far away that they look like they're not moving. But all these brighter white points are the stars that are in the Andromeda galaxy, and that you should have seen sort of shift across the screen in that direction. Anyone notice the time clock? So these motions are so small that you have to wait very long, or you have to have really good technology to be able to figure out how you measure that minuscule difference of the motions or locations of those stars in these fields of data, depending on which galaxy you're looking at. So this is the point where I like to give the analogy coined by one of my very good colleagues, who figured out by doing some math that measuring the proper motion, this drifting of stars that has been, of course, exaggerated for you so that you can actually see it with your eyeballs on this screen. Measuring this proper motion is like watching human hair grow at the distance of the moon. No telescopes, no binoculars. You have a friend, your best friend staying on the moon, and if you could see their hair growing on their head or arms or whatever. That is what we're talking about. So we're talking about micro pixel scales on instruments to see how the motions of, or the positions of these stars are changing, to get that other two dimensions of velocity. All of that just to put it in the beginning of my orbital models. Okay, so it's quite a great thing that we've been able to figure out, mostly my collaborators, not me, how to do this kind of measurement. And now we have that available for many of the other satellite galaxies in our local neighborhood, because we've learned that this technique works. We've learned exactly how long we have to wait between the two sets of imaging to get a good result that we can actually detect. There's of course other parameters that matter as well, but the distance and timing is one of the main ones. So I said that already, but here's your fun little graphic of proper motion on Andromeda. It's like watching human hair grow at the moon. So quite a fun one to drop on folks when they haven't ever heard of this measurement and how difficult it is to do it. So once we have these 3D motions and 3D positions, like I said, that is where I can finally put them into the models that I very basically described for you, and integrate those equations of motion in time to arrive at results like this, that tell us, for example, that this is only representing a couple of the dwarf galaxies around Andromeda. You can see some really nice shapes. They make kind of like a floret pattern. You see some ellipses. This green dot is showing you the current location of that satellite galaxy. And so if you were following its trajectory, you would follow it backwards here, and it would go back somewhere over here. So now we have a sense that this galaxy came from this rough three-dimensional volume relative to the Andromeda galaxy and how it's oriented to the projected disk of the Andromeda galaxy. The other one that's shown in blue is actually a companion satellite. So these two on the sky, I know they don't look like it in this projection, but on the sky, they look very, very close together. They're separated by only 1 degree on the sky. And so the long-standing theory has been that those two satellite galaxies have been interacting with each other over time as they both orbit around the Andromeda galaxy together as a pair. And what we showed is that actually can't be true, because it looks like when one of those galaxies is getting close to the Andromeda galaxy, the other one's actually far away from it. So they're exactly out of sync, out of phase. So the features that we see in those two dwarf galaxies, we have concluded can't be because they're interacting with each other, but actually because of past interactions with the host galaxy. They just happen to be projected in a very similar part of the sky from our vantage point. We know a lot more information around Andromeda than just these two orbits, so this is also already a little bit out of date. This one's a little bit more of a complete picture. So we now have all of that beautiful 3D information to put into our models for almost all of the known Milky Way satellite galaxies. And so this is showing you just one representation in my orbital models of what comes out as the orbital histories of these different satellite galaxies. So again, anywhere you see sort of a point, that's the present day location of a satellite, and you can kind of trace back the lines to tell you where things came from. I'll go back to a video of this in just a second as well. What I want you to notice from this though, is that there's a lot of diversity in these orbits, right? So as I said very early in this talk, these satellite galaxies are not all orbiting in a plane like the planets in the solar system for the most part. They are not all looking as if they have completed 1 full passage or 2 full passages or 3 full passages around the Milky Way. Many of them are only entering the vicinity of the Milky Way's gravitational field for the very first time recently. Others, they're harder to see in the center, but there are some in the center that really have. They look like they've gone around the Milky Way several times already over a few billion years. So there's a lot of variation in what these different satellite trajectories look like. That tells us a lot of different things. One thing I did not mention, but you can ask me about later, is we can also use the motions of these galaxies to figure out how much mass especially that dark matter mass that we can't measure directly, is actually enclosed around the Milky Way in that dark matter halo. It's a number that we kind of know to an okay precision. We don't actually know it extremely well. And when we build these kinds of orbital models where we want to reconstruct the orbits of these satellite galaxies, you need to understand the fundamental parameters that set that model well in order to get a good answer out. So you kind of have to iterate and go back and forth. You tune one thing, you run another set of models, you tune another thing, you run another set of models, and you make a conclusion based on all of those results together. So the things we can learn, so this again on the left it's the same movie I was showing on my title slide, just in a different color scheme, but this is still representing the Milky Way's satellite galaxies. But some of the things that we've been able to conclude by doing this kind of science and figuring out where these different satellite galaxies were at different points in time is one, like I said, that all of these satellite galaxies are not orbiting in a plane. They're doing all kinds of different, following all kinds of different motions and trajectories. They're all at different places in their trajectory relative to the Milky Way. Again, some have completed an orbit, some have completed multiple, some haven't yet even completed one. They have all of these different shapes to them. And then my most fun set of conclusions that I like to end on is that we have learned that satellite galaxies have their own satellite galaxies as well. So one thing I'll point out in this image that I go back to here, if you can see these two thick white lines, those are representing the orbits of the Magellanic Clouds, those most massive and brightest satellite galaxies around the Milky Way. If you can see closely, there are a handful of lines that look like they're sort of intertwining and braiding around those two thick lines. We think that there are a handful of these very faint satellite galaxies that were already in their own little group. And then all of those in that group came into the vicinity of the Milky Way together, only very recently for the first time. So we can now start to see all these little individual structures of smaller groups of galaxies entering larger groups of galaxies. There's of course interactions happening in that smaller group of galaxies that changes their properties over time. Then they're entering into this larger gravitational field where there's a lot more going on. So they'll continue to evolve in all kinds of other different ways. And so we've started to be able to pick out all this different kind of structure in the motion and evolution of these galaxies, which helps us understand, again, remember, things all the way back to what early conditions in the universe are, because these galaxies are all mostly very old and formed their stars very early in the universe. So we can start to make a connection from looking at the things nearby, tracing their properties, and making some inferences about what happened a long time ago and how they came to be. So that will be the end of my science talk. I will tell you for 2 more minutes a little bit about a program at Villanova that I'm a part of. This is not the end of my science. This is the actual last slide. I've showed you so far how we can rewind the orbits of galaxies to figure out where they were in the past. We can similarly run these models into the future and figure out when galaxies are going to merge with each other. And so this is a story that comes up every few years as people make new advancements, but you probably know that the Milky Way galaxy will eventually crash into the Andromeda galaxy. And I worked with a team of my colleagues back in 2019 when we got revised proper motions, now that you know what that is, for the Andromeda galaxy to take another look at that question. For a long time, it was said that the two galaxies will hit head on. In our revised results, we found that it might be more of like a glancing sideways collision, not a straight head-on collision. And we did account for also some of the satellite galaxies that live in the vicinities of these two galaxies, namely one of them being Triangulum. It's not pictured here. We also accounted for the gravitational influence of the Large Magellanic Cloud. Turns out it changes the numbers and the timing of when this collision will occur. But this is just to say that we can also use these models to look ahead and figure out how galaxies will continue to move and merge and interact with each other over time. It is not just a one-way time axis. Okay, now I will tell you about a little bit about our One Sky Center for Astrophysics at Villanova. This is a center we just opened last year in April of 2025. The whole purpose of this One Sky Center is to unite all the people working on astronomy at Villanova. So we have a Department of Physics and we have a Department of Astrophysics and Planetary Science. So this is meant to be a place where all of us can come together, really put our heads together and hopefully do a lot of work that can not only benefit our science and help push science advancement, but also bring it back out into the community. So I am here as one of the One Sky faculty members. Like I said, it's an interdepartmental collaboration. We're trying to build on the astrophysics programs that we have going on to help students broaden their experiences, bring them to local attractions like the Franklin Institute, and expose them to volunteering opportunities where they can take all the knowledge they learn in the classroom and come talk to elementary school students. and really help to build the next leaders of science and astronomy as we move forward. So I won't read this all to you, but if you want to know things that we're doing and things that are upcoming, here are a whole list of things that we've done so far. We've worked with high school students. We are trying to build a STEM cohort through the Women's McNulty Institute. We have some workshops. And we are starting to plan some more community-oriented activities. We'll be having a 1 year of One Sky celebration soon. We hope to have a One Sky Day that will be open to the community and have lots of demos and experiments. And if the sun is out, some solar filters on telescopes, we can do some observing. But if you're interested in learning more about what we're doing at the One Sky Center, I'm just going to leave you with this QR code so you can take a look at upcoming events and stuff that's going on just down the road. But I will thank you for your time, and I'll take more questions now.
All right, thanks. That was a great talk. Any questions?
I don't know if I missed it, but how are you actually figuring out the proper motion?
Yeah.
Because, on your thing, obviously it is a large time scale.
Yes.
So, how are we doing it in these short time scales?
Right. So the movie was very exaggerated just so we could see it on the screen and detect it with your eyes.
Yeah, I got that.
We're doing this with the computer algorithms, right? So we know to a very small precision where these stars are lighting up pixels on a CCD, and we can take the image, compare it to the other image that's only taken in reality at a time baseline of 5 or 7 years or 3 years in some cases, and then differencing those images computationally. So that video is only to really get you a sense of how small this motion is, because if I showed you the real images, they would just look identical to you, because the pixel scale motion is very, very small.
So, in the kind of detectors and the pixels
Uh-huh.
that you use. Like,
Yes. Yeah.
what size are we talking about?
Oh, I don't have specs with me right now, but that's also why I'm not the observer. I mean, these are like the best cameras that exist on the earth, right? They're giant CCDs.
So
with many
they're
thousands of
probably
thousands of
very
pixels.
small pixel things.
Absolutely.
And
Yes.
even over, let's
Yeah.
say, a 5 or 10 year,
Yeah.
it's able to detect them.
Yes, and I think the motions in the Andromeda Galaxy are something like, the motions are changing by like 1,000th of a pixel. So even at that scale with really high resolution, extremely small motions. Yeah.
Makes sense.
I don't know who was next, but you've got the microphone, so I'm gonna let you pick.
Minute satellite galaxies and globular clusters.
Uh-huh.
How do you tell them apart?
Yeah, good question. So I touched on this very briefly, but I did not show you or talk to you about it in detail. So like I said, there is a mass overlap in the range of masses where you find globular clusters and the range of masses where you find satellite galaxies. One of the main differences is if you compare the velocities of the stars in those galaxies, and by that I don't mean their 3D motion relative to us. I mean, how are those stars moving relative to each other? There's something we can measure called the velocity dispersion, which essentially tells us, are those stars all moving very coherently in the same way? Or is there some spread in how those stars are moving relative to each other? So something we call the velocity dispersion. And if you can measure that property, globular clusters have a very distinct range of velocity dispersions, and galaxies have a very distinct range of velocity dispersions because they have that extra dark matter mass in them. So globular clusters do not have dark matter, and so therefore their internal motions of stars look very different. Yeah, so there's a nice sort of set of properties where we can make a figure and kind of draw a line straight through it where it separates out globular clusters from satellite galaxies. Great question.
Just to follow up.
Yep.
What Sandy was
So when you're,
I can repeat it.
yeah,
Yeah.
so when you're measuring the change in, let's say, the pixels,
Mhm.
you must also account the fact that you are moving at 600,000 miles.
Oh yeah, you've got to account for all kinds of things, right? So yeah, so the question is when you're measuring the proper motion and looking at the pixel changes, you've got to also account for the fact that we are moving as a galaxy, we're rotating around the sun is moving, right? The whole solar system is moving through the galaxy. Yes, there are many motions that we have to also subtract off so that we are actually truly measuring the absolute relative motion between us and the stars in that galaxy. So yes, it's not just a simple subtraction and then you got your 3D velocity. There's a very careful set of corrections you have to apply based on all of the other motions that are also occurring simultaneously.
Our motion would be probably higher or relative to the other one?
I can't do miles per hour, kilometers per second conversions in my head very quickly, but our motion is faster. Yeah, it is significant for sure.
It's faster.
Yes, yeah. Our motion around the sun, I will say, is one of the most important things that we have to account for and subtract off of those measurements.
But it's also in 3D, right? So.
Also in 3D, yes, indeed, indeed. So all those other motions, we also have to know very well in 3 dimensions, right? Yes, good question.
So, I don't think this is working.
That's okay, I'll repeat it back.
So on the topic of stellar streams,
Mhm.
and how they apply to satellite galaxies, we can actually look very close. There are a lot of stellar streams that are in the Milky Way and very close to us. For example, the Arcturus stream
Mhm.
ranges from 1,000 to just 30 light years away from us. So I
Mhm.
was wondering how that applies to things more far away and if that helps us at all.
Yeah, so the question, if I summarize it a little bit shorter, if I caught the whole thing, is that we have all these stellar streams that are remnants of these dwarf galaxies or satellite galaxies that are falling apart as they're being absorbed by their host central galaxy. And we can indeed observe many of them. And we're also in the process of finding many new ones as time goes on at a very fast pace. Similarly, because the same kind of detection algorithms are needed, so we're doing a better job at finding them. So the question is, how can we use those to study similar ideas and questions that we're trying to answer as we are with the satellite galaxies? Is that close? Yeah, so stellar streams are extremely helpful as well. They're a little bit more complicated because they are breaking apart as they are orbiting their host galaxy. So that is yet another piece of physics you have to account for. But there are whole people who have committed their careers to doing what I do for satellite galaxies for stellar streams. So it's absolutely another very hot topic that people are studying very deeply. I'll say that they are interesting in a lot of similar ways in that they can answer the same kinds of questions in that, for example, they're also tracing the dark matter halo of their host galaxies as they're disrupting over time, because you can see the stellar stream and that path will follow based on the gravity of the mass that's internal to it. So there's a lot of similar questions you can answer. There are also different questions you can answer with stellar streams compared to the satellite galaxies. So there are a whole other classification of interesting objects that people spend much of their time thinking about. Yeah.
Oh, there we go. Dead battery free of charge.
Recycle it.
When you're tracing the path of a satellite
Uh-huh.
galaxy,
Yes.
you're using the stellar stream.
Uh-huh.
Do you have to also take into account all the other interactions of all the other galaxies? And
Yeah.
as a result, can you do that with computational equipment you have, or do you need like massive computer
Yeah.
calculation?
That's a great question. So I think everyone heard it, but essentially we have this whole system of satellite galaxies. Are you tracing the path of just one at a time, or are you accounting for all of the other simultaneous interactions that are happening too? I'll give the short version of this answer, but I've spent a lot of time trying to figure that out. I will say in brief that you cannot ignore the Large Magellanic Cloud because it is about 10% the mass of the Milky Way itself. So its gravity is substantial and influences the orbits of all of those other lower mass companions. That being said, you do have to account for the mass and gravitational field of the Large Magellanic Cloud as it orbits around the Milky Way, in addition to the Milky Way's mass and gravitational field. For the most part, you can kind of ignore the gravitational field and interactions between all of those other lower mass companions because they're so small and their gravity is much less substantial. Yes. Now, let's say there are two, even of the really tiny things interacting with each other, right? Especially if they're out kind of in like a distant part of this volume. If you have two satellites that are even very low in mass, but they're out here and it looks like they're going around each other and they're coming towards the Milky Way, then there's a case where you might have to actually account for their mutual influence on each other in addition to what the Milky Way will do to their trajectories. But in the grand scheme of all of it, you cannot ignore the Magellanic Cloud, the Large Magellanic Cloud, and in some cases, the Small Magellanic Cloud as well. But the other mutual interactions are much less substantial. And so they're only gonna change your orbits by a very small amount. Yeah. I will say one more thing, which is that I did not show this and I very much simplified my orbits when I talked about it here, but I mentioned how we kind of model this dark matter halo as a sphere. And in many of my early models, that is indeed what we do. However, one of my collaborators has run a set of simulations that shows us how that Large Magellanic Cloud, which is very massive, right? 10% the mass of the Milky Way, how it actually makes this spherical distribution non-spherical. And so now we're starting to integrate these orbits and trace out their paths, accounting for the fact that this dark matter halo around the Milky Way is actually a very oblong, irregular shape. And that changes the orbits. So there's a lot that we're building on as time goes on. What I've shown you is the most simple form of the models. That also means they include the most approximation, right? So we're building as we go and as we learn more.
I have a question about the accuracy or the approximation, considering that some of these measurements are, 50 years apart, maybe.
Not the proper motion ones so much, but finish your question.
How do you project that out a billion years and
Yeah.
have confidence that it's, is it reasonable? Is it just a guess?
Yeah, so the proper motions for the galaxies in the local group, most of those were all taken very recently in that, with the Gaia spacecraft, for example, that is what's measured a majority of the proper motions for the Milky Way satellites most recently and most comprehensively in that it's got the largest data sample. So those measurements are based on data that was only taken in the last like 6 years, like 2018, and the time difference being something like 2023 or 2024. So that time baseline is recently taken, so the methods are pretty modern already. There are some cases where we are only in rare cases able to take advantage of the fact that, the Hubble Space Telescope was launched in 1990. It's as old as me, pretty much. In some cases, it has taken the right kind of data for that first set of imaging for galaxies that are even outside of the local group. And some of what a couple of my collaborators are working on right now is that they found that the quality of these data sets is good enough that if we take another set of images now, 20 years later, from when some of these earlier images were taken, these were not taken right when the telescope was launched, but a little bit after that, that we can leverage that 20-year baseline for galaxies much further than the Andromeda Galaxy, where you need to literally wait 20 years to see the difference in that proper motion. Because the proper motion time baseline you have to determine goes as 1 over distance squared. So the further you go, you have to wait that much longer, and it's not just a linear relationship. It's not just twice as far, twice as long. It's even more than that. So there are situations where we are now able to start leveraging this kind of information for galaxies outside of the local group, but inside of the local group, all of these measurements have happened in the last decade, essentially. So I don't know if that fully answers your question, but there isn't a 50-year time baseline between any of the sets of imaging that we're using so far.
For example,
Mm-hmm.
the galaxies you showed them kind of.
Yeah, interacting with each other. Yeah.
Yeah.
So what about them? How do we know that that is occurring?
Yeah, for hundreds of thousands of years.
Ah, I see. Yes. So we use the proper motions as an input of this is how they're moving right now. And what the models are doing is they're representing all of the mass distribution around our galaxy as we think it is right now. And then what we're doing is we're following, as we account for the gravity between all of these objects, we are accounting for how they will move in response to each other if we start them with an initial velocity. So in that integration, you are updating the velocity with time. So you are assuming that, for example, the mass of the Milky Way is the same over the last 3 billion years, which we do think it roughly is. But we actually, for example, maybe this will answer your question, we don't integrate these orbits all the way back to the early universe at 13.8 billion years ago, because our models will not accurately represent what the Milky Way was like that long ago. So we stay within the regime of where we think we are doing an accurate job of modeling the nearby neighborhood of the Milky Way well, based on what we know about its formation, and sticking in that regime where we don't think the time evolution of galaxy evolution overall is drastically changing the local environment. Does that help? Yeah. There's still some approximations, which is why we still have to keep improving, right? This is not the be all end all. And that's why we're still building on our models and trying to make them better. Mm-hmm.
Thanks. Any other questions? Chris, I have one kind of building on that.
Sure.
I mean, how far into the future do you think you can reliably go? Because eventually this is gonna run into some galaxy we don't know about yet.
Oh yeah, for sure.
The
I mean,
unknowns, is Donald Rumsfeld.
I have not tested that rigorously. I would say in the same sense of how far we go back is fair enough to go forward. But yeah, absolutely. The local environment's going to change. At a certain point, the Milky Way will envelop some of these smaller galaxies. So its mass will change over time, et cetera. And so I would say we go back and trust about the last 3-ish billion years. I would say I wouldn't go that much further than that into the future. Yeah. So whatever we do backwards, we can kind of do forwards, but there might still be some approximations in there.
One more question.
Fudge factor.
Exactly.
How far back do your data sets go that you can use? Okay. Yeah.
Like how far back will I trace one of these orbits?
Or
Yeah, about 3 billion years is as far as I'll go.
20-year data from.
Like what is the longest time baseline that we have used so far to get these proper motion measurements?
Right. When did you start collecting enough? data?
Yeah. So, yes, so for, like I said, for the Milky Way, a lot of those, so I'll say it this way. We were able to do this back in 2012 with data from the Hubble Space Telescope because there was already the right quality of data available in the archive of Hubble Space Telescope data before we even knew that measuring a proper motion was possible, right? So you have to have deep enough data that is in the exact same field that you take again in that exact same field later on. So in 2012, it happened to be the case that there was archival data, is what we call it, available for Andromeda. And then my collaborators proposed to measure or take images again in that same exact field and do the differencing there. And that built on about a 5 to 7 year time baseline for Andromeda. For the Milky Way galaxies, it's only been recently that we've been able to start to do this. So this is with, again, the Gaia spacecraft. So those data sets, the first set of imaging is coming from 2018. So they're not very old in the grand scheme of things. A lot of them, you know, we took data for some of these, Gaia took data for some of these satellite galaxies. In some cases, the satellites hadn't yet been discovered, but Gaia, again, is one of these survey telescopes where it scans large swaths of the sky. So people are on the ground finding some of these new satellites, and it turns out that Gaia has covered that area in the sky. So even if it wasn't intentional, they're buried in the data inside of the Gaia spacecraft survey. Anyway, so it's kind of this back and forth situation of finding new satellites, going back to see if we have the right data for them, et cetera. And so most of it's fairly recent in the last 6-ish years or so, 6 to 10 years, yeah.
All right, anything else? All right, let's thank Hector for a good talk.
Thank you.
Okay, well, thank you very much.
Yeah,
It was a
of
great
course.
talk.
Thanks for having me.
Okay, we'll gonna switch computers here and we'll, but would normally be the first part of the meeting will happen now.
Thank you for rearranging for me. I'm gonna go the other way. That stuff. Feel free to share my email. With me. I didn't flash up that slide, but happy to get in touch with folks if they have questions. All right. My belongings. Thank you all. Sorry. Some music.
Have to wait 5 years.
Yeah, you might have to wait 5 years.
Excuse me for 1 minute.
Yeah.
You said something about Haverford College.
I did, yes.
Or my grandson.
Yeah. There was one of the people who is very high up in the February Observatory, was Professor Haverford, and she's taken on a management leadership role. So Beth Willman was a professor at Haverford for a long time. She left in about 10
That's it.
to start doing some management role on the observatory.
Yeah, I know.
So she actually still lives in the area. She left for a while and then came back, but she is heading up the region. Beth Willman.
Beth.
Willman.
Great talk.
Thank you.
Okay,
Yes, thanks.
it's February. It's been kind of a rough late autumn and a rough start to the year with the temperature, the wind, the clouds. It's snow on the ground, making the sky bright. It's been pretty tough, but here's 2 images taken last month. The one on the right, Steve Haas took from Texas, though. He had the storefront, I think it's called Texas, where he has a remote telescope set up. And Stan took that picture fairly recently from his front of his house, I believe. It's the new setup he's trying out. But for this next part, okay, you can turn the light back on now. I want it back on. Length. There we go. Okay, for this next part, I'm going to need an assistant. So I'm going to ask Jan to come up here.
Glad, I think it's glad she volunteered.
And a little bit behind the time here, but no. Nope. You good?
It's just not coming up. There we go.
Okay, this is a kind of a belated, a little bit belated. It's a thank you to Jan for all her years of service here with the as secretary, vice president for 3 years, president for 3 years. Done a phenomenal job. And this is just these images kind of capture, I think, Jan's spirit and all the outreach she has done with the scouts, the different schools out of Valley Forge, even back during the pandemic with the mask. I mean, so what we have on behalf of the DVAA, they have a little something for you.
Oh, no, thank you.
So open it up.
Yes, sir.
We also got some flowers.
This is craziness. Thank you very much. What is this?
It's not a new telescope, right? 'Cause
That
that rained for a
we need
month.
more cloud.
Really nice. Look at that. It says President of DVA 2023 to 2025. To the Bluebell Inn. Oh, this is an
So, thank you.
unexpected.
So there you go, and you get the flowers too.
Wow,
So that's on behalf of everyone in the DVAA.
thank you very much, everybody.
Well,
Appreciate
you're
it.
now you're welcome.
Beach.
It's a beach.
Being the president is just so much fun. I mean, really, you just get to experience so much of the club, get to know the most fascinating people are in this kind of organization, I think.
So you want to be president again? 3 more years.
That's great. Thank you so much. Appreciate it.
You're welcome.
Well, I put this away already. I didn't want to break it.
We'll pose for you, man. He's over here.
Oh, here?
Oh, he's coming. Okay.
Got it. Thanks.
Okay.
Oh, but that's enough.
Okay. Now on a real change of pace note. Beware of scam. How's that for a segue, huh? That's pretty good. You know, I put this together. I thought about this morning. And I said, what's I doing there? But I already sent it to Jeremy. So I said, well, it is what it is. So, this is not a scam, but evidently there's been some emails going around, either saying it's from Chuck Allen or from some officer of the Astronomical League asking for, like, you know, gift cards and stuff like this. Just be aware, it's all bogus. So that's all I want to say. They asked us to announce it. Okay. Here we have coming up March 3rd, total lunar eclipse. Now, this is an interesting one because it happens when it's total, it's quite low in the sky. And it happens, if you notice, very early in the morning. If you're an early riser, this eclipse is meant for you. Basically, you're going to get a really good western horizon. The partial eclipse starts, which is where you start noticing the chunks going out of the moon at about 4:50 a.m. And totality is not until 6:04. But the moon is only about 5 degrees above the horizon. That's not much. When totality begins, that's that beginning of civil twilight. But it should look pretty neat. If you can find yourself somewhere where it has a good horizon and get out there, it could be an interesting event to see. So we have a little cat and mouse going on here with Saturn and Venus on the 7th and 8th. On the 7th, Saturn's a little bit above Venus. You can see it. It's good to use binoculars for this because Saturn's real, because Saturn's not that bright and it's getting into the twilight. So the next night you can watch, if you go back-to-back nights, if we were to have 2 clear nights in a row, which is quite an if, but if we did, then you'd see Saturn slightly to the lower left versus to the upper left. So that could be something fun to see. Once again, it's a Jupiter prime time. It is up. Now, hopefully, the worst of the cold is behind us, hopefully. And so we'll be able to get out there and start, observing again. We got a couple clear nights. March can be a pretty nice month after what we've been through. So Jupiter's still prime time. You can still check out where all the moons are going to be and that sort of thing at this web address here, thesky.com, Galilean moons. And one more, I mentioned those 2 of these last month at prime time. This is Algol again. These are kind of fun to see. Now, you'll think this isn't that big of a deal, but it's kind of neat to see how the constellation changes in appearance. It looks totally different when the star is at minima, which is only for a couple hours. In this case, on the 16th, around 8:50, each in daylight time, 8:57. And it's really noticeable. If you go out sometime before then, look at Perseus up there. It's a pretty easy constellation to see. It's one of the brighter ones, so it's one of the ones we can pick out, here pretty easy with our skies. And but then if you catch it before then, they catch it, close to this minima, it really makes the constellation look different when the stars just suddenly drops out. And it's one of the brighter stars. It's like a 2nd magnitude star, so it's pretty bright. And suddenly it goes quite a bit darker. And this March is always the month, really, one of the prime months for the winter constellations. In November, they kind of rise pretty late. December, January, February, it's a lot colder usually, and they're well placed, but it's very cold. March usually doesn't quite have that biting cold. And it's a good chance to check out while they're still high in the sky. This is at 7:30 Sunday night, and see Orion's right here. There's the meridian, the north-south line there. So it's real high in the sky. You have, all the, still have Taurus up high, and you've got Auriga up here, and you got, Jupiter and the Gemini up there. And it's a really good time to check out the winter constellations. Okay, we got a boatload of stuff coming up. Okay, first off, indoor clinic. That is here tomorrow. Goes from 12:30 to 4:30. We're going to cover an hour on, we're going to cover, I'm not sure the exact time frames for all of these, but we're going to do planetary type photography, how to capture planets through your telescope. We're going to do lunar photography, deep sky photography, and we're going to have an experience from a member who's only been doing this, Brett, for about a year or so. And his experiences, all his joys and his shocks and his blunders. It's like, because that's what you have with astrophotography. You're going to have successes mixed in with some not so good. But he's going to tell about some of the pitfalls and maybe help people avoid them. So that's tomorrow here. Now, if you can register tonight, but if you didn't register, still just come. If you can make it, you think you can make it. It's on the website. You can look at the events calendar on the website, and you can see. How the time slots are broken down. If one of those items looks more interesting than others, you can know when it's going to be covered, and you come in for that 1 hour period or whatever it is. And then on the seventh. Now, this was one that was going to be January 31st. It got postponed because Gary was not well, and so we stayed home and we postponed this one. And we got it rescheduled for the 7th. That's a week from tomorrow. And it's on how to navigate the sky using Sky Safari, Stellarium, and Star Chart. And this is a really good seminar. If you want to learn the sky and how to find things without hitting the go-tos and things like that, and just navigating your way around and how to use these different tools. And Gary will go over, how to use them just for looking up and seeing things, but also how to kind of customize it for your telescope or binoculars and what field of view you see, so you can kind of use it to guide yourself to find objects without the go-to. So that's the 7th. But that's just kind of newly announced in the last couple of days. So, but you go online and register for that. That's on the events again. You go down to the events calendar. There's a register button. We're going to need we need at least 8 people to hold these things, or else we put the kibosh on it. Right now we have 5, so we need at least 3 more for this to happen. So
We got 4 last night.
got 4. Okay, so we're 9. Okay, we're 9 now. Okay, but still, sign up. That doesn't mean you're off the hook. Okay, Hibernia Park. I want to talk about this one a little bit because this is a collaboration between the Delaware Valley Club and the Chester County Astronomical Society. Ken, who is our outreach coordinator, has moved to Delaware, and he's meeting some new people and stuff. We're getting a little more cross-pollination here between our groups. And this is kind of an interesting idea because it's a combination star party with the Chester County group plus our group. And this is the kind of thing I think is really good because you get to meet some new people and what their experiences are with the club. It also helps out because it's a stronger group for people who are visiting, coming out to see it. And so we really need, if you can make it on the 7th, night of the 7th, is on the website again and the events thing. And he sent a few emails out on the groups IO. But check the events calendar, and we'd like to get as many DVAA telescopes out there as we can to show that these collaborations can work. Now, I know it's March and it's a little cool, so it's kind of a little more of an extra challenge, but if you can do it, it'd be great to do. And then you have a Messier Marathon. For those who aren't familiar with what that is, Charles Messier was a French astronomer who was a comet hunter, and he made a list of these. Well, he didn't make a list of all of these, but now there's 110 objects in his list. And at this time of year, usually March is really the key time. It's possible if you start right at sunset and keep going throughout the night till right at sunrise, you have a chance of seeing every single one of those objects. And it's always kind of a challenge, kind of a fun challenge where you get out with your scope and just try to see as many of these as you can to kind of, just to see how many you get. Can you get 80? Can you get 50? Whatever. And this is going to be held at the Muddy Run Observatory in Holtwood. There's a big observatory out there that's kind of administrated partly through the Rittenhouse Astronomical Society. But it's open to everybody. You can bring your scope out and just join a group of people who are as crazy as you are and are going to stay up all night and hunt these things down. This always seemed like it'd be fun. I've not done one of these. I've done like a partial one, but this sounds like a lot of fun, actually. This could be really cool.
Tom, Ryan Observatory is a great facility. They have pretty dark skies there. Holtwood is in Lancaster County, so it's a little bit of a drive, maybe almost an hour and a half from here. But one of the beauties of this facility, it's also a science center right there. But they have an outdoor amphitheater with a gigantic screen that's set up in between the 2 observatories. So the public can actually sit in the amphitheater.
It's a live
outdoors.
display from the telescope. They got cameras going out to show one of the cameras from the telescope's views. So it's a neat facility. I've not been there myself. I've always wanted to get there, and I will get there this spring. But maybe for the Messier.
Excellent.
So we have that. 24th, Anderson Farm Park Star Watch. This is one we do every year. Stan Williams usually heads this up. Once again, all the details are on the events calendar. This is a good one to support. They've had good showings in the past. So if you can go out for that one. All these star parties, we always need as many scopes as possible. Just makes it more fun for the public and everybody who comes out the door. Next, the 25th, the 2 days, the Wednesday before the next meeting, we have our monthly astrophotography workshop. I've got one other slide on that coming up. It's a Zoom meeting. 27th, we have our monthly meeting here. And then we have our first public Star Watch. I call them Star Watches, not Star Parties this year. Just to make sure the public doesn't get a different connotation of a party versus a Star Watch. This is you register as you go, kind of, you register for this. But it's our first one. It's late in March. We had one early in March last year, but it's late in March, so it shouldn't be that bad temperature wise.
So we're not having the keg anymore?
No more keg, no. Well, that's in the back. I'm gonna ask Brian to come up and just.
So work.
Funny what a new battery will do.
Yeah.
That's right. My name's Brian Lee. I'm the welcoming chair for the DVAA. A little light this month. We have 2 new members, Mary Callens and Dilip Patel. I don't believe that either of them are here tonight, but I heard Dilip might be at the meeting or at the thing tomorrow. So let's make them feel welcome.
Okay, next, Joe, did you want to, oh yeah, there you are. Our loaner equipment. That's funny, that star above the P looks like a dot, doesn't it? You notice that?
Very European.
Yeah. Right there.
Yeah. Hi, folks. Oops. Hi, folks. I'm happy to report tonight that the DVAA has acquired its 3rd smart telescope. This is a dwarf mini, and it has been made possible by the generosity of one of our members. So I'd like to thank that member who wishes to remain anonymous. But this scope is very, very light. I'm going to read the specs real quick for you. It weighs 840 grams. It is really small. It has a 90-second shutter, auto go to precision, 1-tap processing on your cell phone or tablet, 4 hours endurance, 3-minute setup, 3 built-in filters. It does internal calibration and multi-night stacking. So it is really a great instrument. I was on their website this afternoon. The images are marvelous. So it is available. It also comes with this little tiny tripod. So my thanks again to that member for his generosity. So thank you.
Thanks, Joe. Okay, it's a little more. We have the DVAA workshop we're talking about is on the 25th. That's the Wednesday before the normal club meeting. And this next coming month's going to be an open show and tell type question answer session. Gary decided on this because we're coming off the clinic tomorrow, and there might be a lot of questions generated from the clinic. So we figured anybody who wants to have more questions or have thought of things after they left the clinic tomorrow. Everybody's welcome here, from the person who has just thought about, astrophotography, can't even spell astrophotography up until you have a scope in Chile that you're doing, 20-hour exposures on. So there's a real range of experience here, but it's a nice group. Everybody helps everybody. You learn a lot in these meetings. This is how you find. This is how I find with all the events we talked about. Just go to the homepage. You go to events. Hit log in, so you see all the events, the members' events, And this is where you see like the Anderson Park and the Mesier and the clinics and all that sort of thing. So, and there's a link. When you click on it, you get a link for the Zoom meeting. So that's how you navigate your way. The last, you haven't forgotten to renew, have you? Anyway, basically, if you had a membership in 2025 and you have not renewed, in about 2 days, you will be an inactive member and won't, when you log in, it's going to say, hey, you have to up your dues order. You won't be able to see the member events coming up. Anyway, if you haven't and you want to, now's the time. Okay. And now that comes to the observer report, the NOVA and M31. This is where Gary Trapezzano is going to come up here and talk about that for this month's observing.
Thank you. The clicker will work.
Yeah, down is up.
Okay, down is up. I know, it's always backwards. Where's the,
Okay. Hey, look at that, it's working.
Okay, thank you. I'm Gary Trapezzano. Oh, you want to do the lights? Yeah. I'm Gary Trapezzano and, okay, there's a thing. And I'm going to be doing the observing talk tonight. And tonight's topic is going to be the NOVA in M31, AT 2025 ABA0. If you remember at the December meeting, Tom briefly talked about this and showed a picture that I had taken of the NOVA, and then also talked about Koichi Itagaki, who is the person who discovered this NOVA in M31. So I'm going to take that a little further and explain how kind of I got involved with this particular object and wound up taking that picture. Tom had mentioned that I sort of took it by chance because only having one night available of clear skies. And I thought, well, it's well positioned. It's up all night. I'm just going to shoot that. I haven't taken it for a while. So I'm going to go into a little more detail with that. So before we do that, though, the NOVA AT 2025 ABAO was discovered on October 17th, 2025 by Koichi, and it's considered a luminous red nova. It's a relatively rare type of nova caused by a partial ejection of a binary star system's common envelope, and then the merger of those two stars into one. The luminosity of a luminous red nova falls somewhere between that of a supernova, which is really bright because the star creating that basically blows up and then goes away mostly. And that of a nova, which is dimmer, which is more of a transient event of a star, and then the star will return back to its sort of dormant state. The visible light of a luminous red nova can last for a couple of weeks or a couple of months. And this is according to Wikipedia. It is a distinct red color, becoming dimmer and redder with time. And that distinct red color is an important point we're going to go into in more detail. Because what happened was, as people were imaging this and people were observing this early on, they weren't seeing it being red. In fact, my image that Tom showed, and we'll show that close up, shows it being blue. So why is that? So here's what I was up to while Koichi was discovering this object. Tracy and I were up at Robert H. Treman State Park, which is southwest of Ithaca. Yeah, Brian, I know you. Brian's from that area. And we were doing some hiking. We took the van up there. It was near New Moon, so we knew that the skies would be dark. So I had a telescope sitting in the van or two. And we did some hiking during the day. And then at night, the first night we were there, it wound up being a clear night. And it looked like it was going to be the only clear night for that part of our trip. So I set up a telescope, actually not even a telescope. I took a camera lens, a 200 mm camera lens, hooked it up to my astronomical camera, and decided to shoot M31 just for the heck of it, wide field. I thought it was, again, it was well positioned, and I thought I have it there. I'll shoot it till the battery runs out in my little external battery. It was about 30 degrees, 29 degrees, so the battery didn't last real long. So I got a couple hours worth of data of M31, very wide field. And then about 4 days later, I'm up at Cherry Springs, and with Craig and Tracy here, Brent and his wife Jennifer, and same situation. Now we're here for another 3 days. The first night's going to be the only good night. So we set up some telescopes. It was a particularly good night, if you can tell from the wait, what am I doing here? Oh, there it is, from the sky reading. That was around a little bit off of zenith, a little bit away from the Milky Way at around midnight. So it was pretty dark. And I had my mono camera with me with my TV85, and I said, I'm going to shoot M31 again because it's up all night, just like it was 4 nights ago, and I'm going to get some good data. I never shot it with a mono camera before. So I shot 7 hours and 37 minutes. I did it from as soon as I could set up until the sun came up. And that was the picture that I got. I also had a 100 mm lens that I wanted to test to just see how well it worked with an astronomical camera. So I also shot some really wide field. This is M45. This is 13 degrees by almost 8.5 degree field of view. So really wide field. This is M42 here, the Running Man. This is the Belt Stars and Orion, Rigel, the Witch Head. So this is the same kind of thing, almost 14 degrees by 9 degrees. And that was it. I didn't think much of it. Well, a month later, we're going to get back to the nova now. A month later, I wind up at Cherry Springs again with a different set of club members, as you can see in this little selfie here that Tracy took of us. And this is November 18th to 21st, so almost exactly a month away. Well, on this trip, it was going to be cloudy every night. In fact, it snowed one night and it rained and it drizzled. So we were just basically in the lodge, hanging out, talking, having fun. And on Wednesday night before dinner, I happened to check email, and I saw this email come in from Al Lamperti, who keeps us advised of lots of things like this. Wednesday, November 19th, he sent it in the morning. I saw it probably 12 hours later. And this caught my eye. There was this nova discovered on the 17th, and you can find out more information by following these links. So I followed the links, and I went to Kyochi's image here, his discovery image, and I got this, and I thought, okay, that doesn't do me a whole lot of good because I don't know M31 that well. And that's a pretty small scale. You can see here, in fact, I have an arrow to it. You can see there where the nova is pointed out from his discovery image. There was another image that Kyochi had there, and that one just showed the same image, same field of view, and then the normal non-reversed view of it. So that didn't do me much good. But then there were other images. If you look at that, there are other people there, and this list goes down. There were probably maybe 10 or something at that point. Or no, probably more like 20 or so. I found this image. This was actually shot with a Dwarf 3, just to put it in perspective. So a little all-in-one telescope, a Dwarf 3. But this one at least had a blow-up of the area of M31. And then it had the star highlighted, and then some field stars in that area that you could then navigate to. So I thought, oh, this is great. We ate dinner and I couldn't wait to get back to look at my M31 image. So before we went to bed, then we were talking and everything. Well, before we went to bed, I thought I need to do this before I go to bed because I'm going to be laying there all night wondering if it was in my image. So everyone's going to bed and I'm sitting at the kitchen table with my laptop and I pull up my image and I had it oriented like this because that's how I shot it and it fits better on my computer screen. In this image, north is kind of to the right. In normal images, when you're doing like astrometric kind of stuff, north is up, and that's a convention that's fairly commonly used. I was so excited, I didn't even flip the image. It would have taken a second to flip the image. So I'm sitting there with my image this way, zooming in, doing this, and struggling with this, but it was there. If you look here, that's that same area. You look here, and you look there, there's the nova. And then I'm up for the next hour and a half because I was pretty excited. I thought, oh, wow, I got it. Well, then I started to think, wait a minute. Oh, I'm sorry. First, I wanted to make sure it was really it. So these are zoom ins. North is up. I finally changed the orientation to get north up. And one thing that I noticed with looking at other pictures is how can I quickly find out like where this is? What kind of like when you star hop, you look for the patterns in the stars so you can get to something. Well, one of the real prominent things that I kept cluing in on was if you look at this group of 6 stars here, it's kind of like a funnel or kind of like the end of a horn. These guys are basically pointing right to the nova. And then if you look here, there's a little bit of arc of stars. There's a little triangular group here. The nova is always right in that area. So these 2 stars here are now these 2 stars, and there's that little triangle. And you can clearly see the nova sitting in there. And then I thought, well, let me just really double check this. I found one other image that a person had with it fairly close up. I cropped mine to that same kind of image scale, and you could definitely see it is in the right spot. So at this point, I'm convinced that I have this thing captured. So then I thought, well, wait a minute, what about that image from 4 nights ago? I wonder if it's in there. Because this I didn't expect to even see it because it's such a wide field and the image scale is like way mismatched for the sensor and all that stuff. But you can see here, there's that little horn again. There's that little triangle. And right there, you can see a couple stars. So let's zoom in on that. And sure enough, you can see a little bit of red glowing. This is actually was shot the same day it was discovered. And it's actually, from what I can tell, looking at the Julian date listed for the discovery image, it was actually shot a few hours before it was discovered. And I thought, wow, that's interesting. So I wonder how long that was that star was kind of there getting ready to merge and turn into this luminous red nova. So I posted my image. I posted my image of this to the website with those blow-ups, and Dan McCauley went back and he said, wait a minute, I had an image from a month ago. Let me look at that and see what's there. So this is September 27th, so almost, it was 3 weeks before it was discovered roughly. And you can see that there's a little red dot sitting right there. And here, this is the horn again, the little triangle right there. And you can see that luminous red nova, sort of. And he said, well, maybe it's just a field star. Maybe I'm not sure what I'm seeing there. But anyway, this became an interesting tidbit. I had some pictures of M31 that I had taken 3 years previous from Blue Mountain Vista. And you could almost see something there, but it was too much in the noise floor. But it was sort of like, well, there is a star there. there was a binary pair, right, that turned into this brighter thing. So then, this is a zoom in on Dan's. So then Dan said, well, why is yours blue? Because this is a luminous red nova. I don't know if what you have is correct. It shouldn't be blue. It's supposed to be red. And I thought, oh, yeah, it sounds like you're right. Let me look into this. So I actually went to my mono data. I looked at every frame. I looked at the subs. I calibrated them and then extracted the RGB channels, looked, and it was absolutely blue. There was no doubt that the data that I had, to the best of my ability to do photometric work, which is fairly straightforward nowadays with some of the software tools, that the blue channel was absolutely the hottest channel of that data after the data was calibrated. And it's calibrated against the Gaia star database, which is like some of the same stuff that our guest speaker tonight talked about. So I started to think about this more, and I found some papers. I started to dig deeper into this, and the official, this is a technicality, the official date of discovery was actually the 19th. And it's because it needed to be verified. So even though that's the official date, the first advisory of a brightening was from Koichi, and that was done on the 17th. But there were even some earlier pre-discovery measurements that were done on the 14th, and there are even some earlier. Look at Dan's a month earlier. So remember, this is all relatively new. This is a month-old information of an object that doesn't happen real often. So people were still trying to scramble. What does this mean? What are, sort of the luminosity curves over time, all this stuff. And Mark Ferrari also jumped into the mix, and he said, hey, I took it on the 20th of November. And he said, but I also shot M31 on the 13th of December 2 years earlier. And this is that area. Now, if you blow that up, you can almost see something there. This is the noise floor, so it's not much above the noise floor, but something is there. And again, there should be a binary pair there, but it's another galaxy, and you're shooting this with a small telescope from our planet. So it's like, are you really seeing is this real, right? Am I really seeing this, or is it some either artifact or some field star that's in the way? So this became this is a bit of an interesting thing now. So getting back to that blue color in my image, again, from the Wikipedia, visible light can last for months is a distinct red color. Well, mine's distinctly not red, it's distinctly blue. And then Tom had done an AI thing. He mentioned it in his talk, and then we were joking about it. Well, you know how AI is always right. AI said, when Tom Googled that a luminous red nova appears blue during its initial high energy phase because the temperature is very high, and a significant amount of the light is scattered, just like skylight, right, as the blue scatters. And this blue peak is short-lived. So if you look at, again, my Cherry Springs image, and it doesn't show up as blue here as it does on my computer screen, but this is certainly not red. And when you look at it, there's a lot of blue content in that. So that's my image again, blown up. And then Wayne shot it on the 25th of October, which was 5 days after the image I just showed. And then he also shot it again a month later. And this was shot from Green Lane. Conditions were fairly similar. You said the nights were a little bit different from one another in terms of haze, but same equipment, as apples to apples as you can get depending on the weather. And you can see here that this clearly has a different hue than that. When you really look at it, I zoomed in on them. When you really look at it, you can see much more of a red hue here than this one. Looks whiter. And on a computer screen, it's even more evident. So that also indicates that maybe there is this shift over time, and maybe AI was correct in that sense that initially it is blue because it's hot. It's this new event. So in doing some digging, there's the science basically backs this. So these people, this was originally accepted November 7th, so only a couple weeks after the event happened. But it was officially received February 15th and posted. So I found this actually when I was doing some follow-up research for putting this talk together. And it's a very long article that actually goes into a ton of detail. There's light curves for all this stuff. It's really, really well done. And the link was actually in an earlier thing, but you could Google this and it'll come up. But in terms of, there's a couple excerpts from this. Color evolution, the intrinsic colors of that nova were blue soon after its discovery, and then it evolved to redder colors after blah, 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 blah. And then they have all the curves to show this. And then it also talks about the light curve. It says the light curve of the transient, they look back historically at that star, at that binary pair. And they said it experienced a slow, long-lasting, about 7-year slow increase in luminosity that was distinctly red before it merged, turned blue, and then after the energy started to dissipate, started to get red again. So it actually went, all of the things that we were seeing and questioning and saying, we can't be looking at this right, we got to be looking at it, actually was proven to be correct, which is just a really cool thing that, you know, we have these toys now, these cameras, these small telescopes that can do this stuff, and how it actually, when you put your heads together, it actually, you were sort of making sense out of this stuff. So some takeaways, some personal takeaways. Serendipity is a really cool thing because it just so happened that it was going to be lousy weather, and I haven't shot M31 in 3 years. And it's kind of like, I think I'm going to shoot M31 tonight. Why not? And then a week later, same conditions. I think I'm going to shoot it again with a better set of toys, with a better camera, and really do a good picture of M31. So the somewhat randomness of me imaging those is a case in point where sometimes it's better to be lucky than good, right? The old adage. Right, Tom uses that one a lot. The other thing is that going down the rabbit hole, and you can see I spent some time on this over the last couple months. Going down the rabbit hole is really fun, and you learn a lot of stuff that you just don't even know you're going to learn. Luminous red nova might still remain a bit of a mystery, but every time it happens, we understand a little bit more about them. And then it does appear that this luminous red nova was brewing for a while before the most significant brightening occurred. And that faint star that was in that location pre-discovery was a sign of that pending lunar red nova. And then last thought is that, in the words of Jack Horkheimer, keep looking up, because if you're not looking up, you're not going to see this stuff. Thank you. Thank you, Cal. Thanks.
Gary,
Any questions? Yeah.
you should have wore your members only jacket for that last one.
Oh, yeah. Yeah, exactly. Yeah. Thank you.
Well, thanks, Gary. That was great. I really enjoyed that. Okay, that brings us to the conclusion of tonight's meeting. Hope you all enjoyed it, and have a safe drive home. Enjoy. Oh, I'm sorry. Oh, not the conclusion. Stay seated. We got the drawing. I forgot about the drawing. Did you bend the one I told you to bend?
We had about 60 tickets. He bought some, so, on the other note, we made sure that, he's not going to favor himself.
I won't,
We gotta get 60 tickets sold tonight, so maybe pick 10 winners.
Okay.
And meet me at the table.
Just the last,
Last
last
three
digits.
digits.
last, we're gonna finish. Okay, 520. 520. We have a winner.
Give me that one. Okay. I'll hold that.
Make sure he's got it, you gotta watch it.
At the table. So maybe at the.
Next one, 501, 501. Never
Okay,
won
yeah,
that.
another round.
Okay.
Yeah.
503. Okay,
Okay.
double winner.
Double winner. I mixed them up, so you're not picking yours.
Yeah, I can't find that one. 536. Okay. Five, 3, 3. 533. Let me look at mine. Look at yours. Oh, I might have it. I got 5-3. There it is.
Fix.
It fixes. Hey, thanks.
That's on the up and up.
No, I could find. 500, 500.
No, think so.
Somebody got 500? Oh, okay.
There we go.
Very good. Good. Where are we at? Why don't you get it?
5, 6. That one. Okay, we're at 6. Well, that was.
Oh, okay. Okay.
Okay.
529. It is me. What a coincidence. Working out better than I thought.